the vegetation can change dramatically. And that really gives us a lot in terms of biodiversity, and it can help us in some ways. Precipitation is highly variable, as you know. We mostly have dry forest type, but closer to the coast and some at higher elevations, we have some wetter and moisture forest types. So yeah, so that topographic variability and climate variability leads to differences in vegetation and fire. So here's a quick look at what you're looking at as a digital elevation model. So it's a model of the elevation, color-coded. Shows you, I think you can see by pointer, but the coastal mountains here, and then the kind of the Siskiyou crest along here, and then the Cascade Mountains over here are the higher elevations with the valleys, kind of interior valleys in between. But that variability in topography really gives us a lot of difference in vegetation and in microclimate and fire regimes. So then this is a look at precipitation. So this is modeled based on actual station data, but then modeled precipitation, annual precipitation for that same area. So you can see that's highly variable along the coast. You know, you're getting 80 inches. Coastal mountains are getting up to 190 inches in some places, very extremely wet. But then you enter the rain shadows of the Illinois River, Red River, which are a lot drier. By the time you get over to Medford, it's only 15 inches of precipitation a year. So highly variable. And the vegetation represents that, reflects that. So here's a quick look at the variation in broad vegetation types. So as defined by that difference in topography and in precipitation and temperature, it's highly variable. You know, each color represents kind of a different vegetation type, from the Sitka spruce on the coast to tan oak Douglas fir forests. You get into more dry Douglas fir, white fir, and high elevations we have mountain hemlock, red fir, etc. So, okay, so now look at what's going on. What are historic trends in some of our climate variables, and what do we expect in the future? So a quick plug. So this is a report that is in press, but it's available for download as a digital PDF. So several people at the regional office, Forest Service, teamed up, so led by Jessica Losky, Dave Peterson, and Becky Gravenmeyer. And they led an assessment of climate change and climate adaptation and vulnerability for Southwest Oregon. So it covers that entire area you see in the map. So it includes all the Rogue River Siskiyou, all of the Umpqua, all of the BLM Medford and BLM Roseburg, and all intervening private lands. So that report is available here. You can go grab it and look at it. It's a very long report, but it has a lot of great information about projected changes to climate, projected changes to vegetation.
Seem to have been frozen, Bill. Oops. We seem to have a technical
Just
problem.
that area I showed you for Southwest Oregon, that partnership area. So this is showing you the trend in temperature year to year with the group. A small increase, but a definite increase. So this is just looking now at Brookings, you know, taking a point location looking at historic climate.
Bill, we seem to have problems with your streaming stopping, freezing at points. Are you? It's tough to tell if you get it. You want to try again?
So are you seeing the slide with the temperature trends for Brookings?
Yeah, there it comes, temperature trends and Brookings.
Okay, sorry, it's slow.
That's
So yeah, so the slide is now temperature trends for Brookings. The graph on the right is for the January to February period. So this is the recent period from 1979 through 2020, showing kind of the anomaly from that long-term average, which is right that zero line. So anything below it would be cooler than normal for that year. Anything above it would be warmer than normal for that period. So again, some years are hotter, some are cooler, but long-term, there's been a slight increase of about 0.2 degrees Fahrenheit per decade. And then if you can see that, the max, that was minimum temperature. So this is January to February maximum temperature, which really doesn't show much of a change at all. If anything, a slightly downward trend. And then if we go to now the June through August, the summer period minimum temperature trends, highly variable again, but if you put a trend line through it, there's been a slight increase of about 0.3 degrees Fahrenheit per decade. And then that same period, summer period for maximum temperature, again, maybe a slight increase or flat. So this really contrasts, I'm not showing this, but the interior valleys, places like the Illinois Valley and the Medford Valley, Rogue Valley, have seen a much larger recent increase in minimum and maximum temperatures, a lot more than you're seeing on the coast. On the coast, you're somewhat buffered by the Pacific Ocean. So that helps. But as soon as you go inland, things have been warming up a lot faster. So now looking at climate change projections for all of Southwest Oregon. So these are the projected trends based on kind of what's called the best case scenario, which is the RCP 4.5. RCP stands for Relative Concentration Pathways, has to do with concentration of greenhouse gases, versus the worst case scenario, which is the RCP 8.5. So it kind of shows the bands and the averages of those two from present day or 2020 out through the end of the century. So it's showing some pretty dramatic increases in temperature expected. So best case scenario, up to about a 3.1 degree Fahrenheit increase on average, but that could be little to up to 7 degrees Fahrenheit. And then under the worst case scenario, about a 7 degree increase, but that could range anywhere between 3 and 12 degrees Fahrenheit. So definitely expecting some increases in temperature from a little to a lot based on how well we do. So the increase in temperature is not going to be equal throughout the seasons. And we're already seeing this. Now this is the projected temperatures by season for all of Southwest Oregon. So this is the projected change, because you can see each bar represents a different global climate model, and then the hatched bar represents the average of all the models. So if you just look at the hatched bar, you can see that winter and spring are expected to get warmer, moderately warmer, but summer and fall, especially summer, is supposed to get much warmer. So not equal throughout the seasons, and that's true throughout Southwest Oregon and the West. So now just projections in minimum temperatures for Brookings, just looking at Brookings as a point rather than all Southwest Oregon. So it's similar to what I just showed you. Minimum temperature for the year is supposed to increase anywhere between 2 and 11 degrees Fahrenheit. That's minimum. And then the next is maximum. Maximum about the same. Increase somewhere between 2 and 11 degrees Fahrenheit, depending on how things go. And now to precipitation. These are now historic trends in precipitation. Sorry, it's in metric. You can see the relative kind of change over time. There are 3 lines here. You can focus on the Rogue River Siskiyou. The blue lines, the other ones represent interior valleys in the Umpqua. So you can see over time it's been highly variable. And the trend line, the dotted line, shows you that we've had some periods that have been relatively wet, some periods have been relatively dry, and right now we're kind of in a relatively dry period. So now this is looking at now recent precipitation trends for Brookings. So this is annual precipitation, so highly variable year to year. If anything, there might be a slight increase over that period, that time period from 1979 through 2019. Okay. So now this is now looking for, that's compared to the interior valleys of Southwest Oregon, like the Illinois Valley and the Rogue Valley, which is seeing a much more dramatic decline in summer precipitation, which is likely leading to drier vegetation conditions and more fire potential. So that's the long-term trend of that same period of precipitation during the summertime for all of Southwest Oregon, not just the Rogue River Siskiyou. So again, highly variable, but if you put a trend line through it, it's a declining trend. So our summers are getting drier. Now this is just looking at Brookings as a point, just to take a point along the coast. A similar trend line, but not as dramatic. Again, highly variable, but maybe a slight downward trend in summer precipitation, but not much. But summer precipitation, as we'll get to later, is going to be really key for wildfire and vegetation change. And again, looking at the projected changes in precipitation by season based on different global climate models, the hatched bar being the average of all of them. So winter, we're actually expecting for Southwest Oregon to get slightly wetter. Spring to get slightly drier, summer to get much drier, and fall to get slightly drier on average. So although precipitation, as you saw, isn't projected to change much throughout the year, it's going to be shifting seasonally. So wetter winters and drier summers. And that has implications for vegetation and fire, et cetera. So this is a quick look at our recent drought conditions, right? So we've been having Western US, primarily California and parts of Oregon have been having a long-term drought. So this slide is looking at differences in what's called the Palmer Drought Severity Index. And really, this is an index of that index over, I think it's a 27-year period from 1960 to 1986, looking at how severe the droughts were during that period using this index. So during that period, there were some droughts, but they weren't that bad and they were relatively short-lived, versus the more recent period, 1987 to 2013, it's showing that droughts have become much more severe over that time period. So a lot more chronic drought. It's definitely a trend we're seeing throughout the Western US. All right, so now a look at our fire history and fire ecology of Southwest Oregon, what it's been and what we expect to change. So this is a kind of a complicated or busy graph that shows annual acres burned on this axis, annual acres burned throughout Southwest Oregon. And here's our time period from 1910 through 2018. And the orange bars are the total annual area burned for that year. So if you just concentrate on the orange bars, you can see that some years like 1910, 1914, 1936, 1987, 2002, we've had some really big fire years with lots of fires, some big fires, but that's been interspersed by long periods where not a whole lot went on. So long periods, decades of very little fire activity until you get to, the early 1990s or maybe late 1980s, where things seem to change, where we're getting a lot higher frequency of big fire years. So that really started with the year 1987, year 2002 with the Biscuit Fire that accounted for most of that area. And then you've seen an uptick in annual area burn with 2017 and 2018 being really big fire years. I don't have 2019 on here. 2019 was extremely small, only about 5,000 acres burned in Southwest Oregon in 2019. So, but there's been definitely an upward trend in annual area burn and in years with a lot of burning going on. So then behind that is the blue bars is the Palmer Drought Severity Index. So that tells you during that water year how droughty it was, how dry or wet it was. So, and using this axis, so anything above, anything positive from 0 up to 4 or 5 would be a relatively wet year, and the opposite for negative. So negative numbers would be relatively dry. So, and the longer the bar means the more extreme it was, either dry or wet. So you can see in some years, like the year of the Biscuit Fire, it was a pretty dry year. So, and then our last 2 years, 2017 and 2018, 2017 was actually moderately wetter than normal. 2018 was significantly drier than normal. So lots of things, it doesn't, just because we have a dry year doesn't mean we're going to have a big fire year, because of course you need to have ignitions. That's another big component. So it really depends on the situation. And then behind that, in the color-coded bars, we have the Pacific Decadal Oscillation, which tends to tell you, it's a kind of a more of a synoptic climate period for the Northwest, or for the Pacific Ocean and northern North America. So during a cool phase, we tend to have relatively wetter and cooler conditions. During warm phase, we tend to have relatively warmer and drier conditions. You can see that during a warm phase, we tend to have more drought. At least it was true during this phase. But during this cool phase, it was maybe more years were wetter than drier, but there wasn't a whole lot of fire activity. Warm phase again, we tended to have more fire here. We entered a cool phase, but we didn't have a really big fire years during the cool phase. But now we entered into a warm phase in 2015, and that warm phase was going to last for another 5, 10, 15, 20 years, who knows. So we're expecting during this warm phase to have drier conditions and more fire. And just to show you that it's true across the Western US. The Western US is seeing an uptick in annual area burn. So this is a graph of annual area burn throughout the Western US from using satellite imagery. So going back to 1984 through 1985 through 2017. So, of course, variable, but with the trend line, there's an increase in annual area burn. This is the entire US, and then this is just one portion of that. This is the combination of the Sierra Nevada, and the Klamath and Cascade mountain ranges in Oregon. So there are several components of the historic fire regime. So when we're trying to quantify what the historic conditions were, so for example, we want to see how departed things are today. There were lots of components of what we call the historic fire regime. So lightning starts fires. So we've always had lightning, but lightning has varied year to year. Some years, as you know, we get lots of lightning and lots of lightning starts. Some years we get very little. And Native Americans practiced burning for at least the last 5,000 years up until recently. So they used fire a lot around their villages and travel routes to manage vegetation, and for a number of different reasons. So, but then with Eurasian settlement, that practice was first curtailed in 1850 and then entirely stopped by about 1900. So we're now missing that component of the fire regime. But then came the early miners, trappers, and settlers, and they did a fair amount of burning. You know, they would set fire to forest to clear it for pasture, and there wasn't much, if any, fire suppression back then. And now we have, of course, very effective fire suppression. So, and during this period, there was lots of sheep grazing and then cattle grazing during periods in the recent past. And of course, now we get into the fire suppression period. Fire suppression in the Forest Service began in about 1920, but really didn't become very effective until just after World War II. And over time has become ever more effective at suppressing fires. Or as we say, excluding fires from the landscape. So this is looking at what we call the fire return interval. So this would be looking at how frequent fires would impact a small area of, you know, maybe 50 or 100 acres, something like that. In the Klamath Mountains of Southwest Oregon, and just the major vegetation types. So oak woodlands had a very frequent fire regime, then dry mixed conifer, also very frequent fires. And we know this by looking at fire scars on trees primarily, but there are some other methods as well. So, and then as you go up in elevation, or you go to wetter areas, up to white fir, that fire return interval can then jump up to 20 to 30. Western hemlock, which tends to occupy very moist to wet sites, has much less frequency. Tan oak along the coast can be very frequent, but they can be highly variable. So the range can actually, throughout the period of record, going about to 1650, can be highly variable. You know, some periods where you get lots of fire, and then some periods where you get very little fire. So this is just an example of some research done from, I think this is a Bolin Lake in the Siskiyou Mountains. So some researchers took some sediment cores out of the lake, and they were able to kind of reconstruct fire frequency and vegetation based on the amount of charcoal and the pollen from vegetation that was in that sediment core. So this is showing you over here, based on that sediment core that goes back to about 15 to 17,000 years ago, it goes back that far. The frequency of char or charcoal in the sediments tells you, the amount of fire that was occurring during that period, and how what they call episodes of fire frequency or high fire frequency were changing over time. We had peaks where you had lots of fire going on, troughs where you had very little fire going on. And over here during that 17,000 year period tells you for different species or genera of trees, the relative abundance of that pollen within that sediment core. So you can see how the Pinus genera was very prevalent 8, 9, 10,000 years ago, and then declined. other ones like the ABs, the firs, kind of waxed and waned in the past. So this just tells us that as climate has changed in the past, so has wildfire, and so has vegetation. So this is a look at the land fire data, if you're familiar with that data set. This is looking at, based on the literature, on what we know about fire return intervals, what the mean historic fire return interval was for Southwest Oregon. So color-coded by year. This is kind of a busy map, but you can see, of course, lots of reds. Kind of the dark reds tells you that the mean historic fire return interval was somewhere between 6 and 11 years. So very frequent fire regime throughout much of Southwest Oregon. And it's not until you get up to the higher elevations in the Siskiyous and then up along the coast where it transitions to much of a wetter climate that the return interval jumps up to 40 to several hundred years. But very, very frequent fire regime historically, for the most part. So now this is looking at departures, how departed our fire regime is based on fire exclusion or recent fires relative to what the historic fire return interval was. So now this is that same data set I showed you, but with recent fires incorporated into that. So this is now the departure from that historic fire return interval. So anywhere you would see, say, a dark blob means that a fire just happened there. So it kind of reset the fire return interval. So recent fire footprints, and then kind of the greens, light green and dark green, is where fires happened in the last couple decades, where it reset the fire return interval, where it's now just slightly departed from what it was. But as you can see, much of the landscape still hasn't seen much of any fire in a long time. Portions along the coast haven't burned in over 100 years. Portions in the interior have not burned in over 100 years as well. So this is showing you what it looked like at the end of 2016. Then we had the two big fire years of 2017 and 2018, which added a lot more black polygons, so a lot more literally black. A lot of fire here with the Chetgo Bar fire, Taylor fire, and a lot of other fires during those 2 years that reset the fire return interval and did actually some good work. But still, as you can see, most of Southwest Oregon is still very red, still very, very departed, dangerously departed, and needs either a fire or some kind of fire surrogate to rebalance the forest. Now this is looking it's modeled what's called large wildfire suitability, which is a data set created by Ray Davis and others in the U.S. Forest Service. So what they did is they looked at the recent history of wildfires throughout Western U.S. And then they looked at the predictive variables associated with those events. So whether it's maximum temperature, summer precipitation, solar radiation, etc. They looked at all the predictors of that, and then based on those, then they modeled, based on where fires occurred, where fires are likely to occur. So this is called wildfire suitability, which ranges from 0 being very, very unsuitable for large wildfires up to 100 being very suitable for large wildfires. You can see the oranges and reds being areas that are likely to be very suitable to fire. And it tells you that the Kalmiopsis is very suitable to fire, and it's had, true to form, it's had lots of fire there. Here down in the Klamath region in California, also very suitable for fire. They get lots of fire there. Applegate Valley, very suitable for fire as well. And up in parts of the Umpqua, some areas up in the Siskiyous, the Cascades, not nearly as suitable. We still get fire there, of course, but this model is telling us what we would expect. So the picture across the Pacific Northwest in kind of our wildfire regime. So looking throughout Oregon and Washington, historically, most of our fires tended to be very small. So this is frequency number by fire size. So very small fires tend to be very frequent. And as you went up in fire size, they tended to be much less frequent. And then just the opposite by fire area by size. So of course, there's lots of little fires, but altogether they don't burn much area. But then the bigger fires, even though you have very few of them, they burn so much area, they're really accounting for the large majority of the annual area burned. Then down here, that's showing you that the Rogue River Siskiyou, circle in red, this compares all the forests in the region, has not really a high number of emissions, whether it's lightning or human, but lots of annual area burned. Same over here. So that shows you that really we're in a category with the eastern forests, like the Okanogan, Wenatchee, that gets a lot of fire. So just to show you that although we're on the west side of the Cascades, we really act much more like an eastern Cascades fire regime. So we also monitor fire severity. Of course, all fire is not equivalent. It varies in severity year to year and even within one fire footprint. So we tend to categorize fires into either unchanged, you can't tell a fire burned there, to low severity, moderate severity, and high severity. So these are the trends across Oregon and Washington of those three classes of fires, all fires lumped together. And that's showing there's not really much of a trend, that the majority of the fire area tends to be in the low to unchanged category. You get about 20 to 25% in the moderate category and somewhere between 5 to 20% in the high severity category. And that hasn't changed through 2008, but there is some evidence that since 2008, there might be an increasing trend in the high severity class. We'll look at that. But what we do know is that our fire season is getting a lot longer. So this is a look at some work, I think, from Tony Westerling, look at comparing the decades across, I think, California and Oregon, that looks at the total months of what we consider the fire season, where you have to actually have active fire activity. In the 1980s, it was here, a little bit less than 1990s, but in the 2000s, I think this is up to 2010, that the months really jumped up. So our fire seasons are definitely getting a lot longer. Okay, so we know, we can tell that fire regimes are changing, but exactly how and why are they changing? So, I've talked about this. So fire activity can be results that are controlled by several things, three primarily. You have to have ignitions, right? So you have to have either lightning or human-caused ignitions, whether that's deliberate or inadvertent. You need to have the right atmospheric conditions. And as atmospheric weather conditions change, the suitability of fire is going to change. And then, of course, you have to have the fuel. You need the resources to burn. So the vegetation itself is a very important factor in this. So of those three legs, those vary spatially across Southwest Oregon, and they vary temporally from year to year and throughout the seasons. So, a combination of that intersection is going to give you the fire activity in any given location and point in time. So first looking at ignitions, this is something I found doesn't include Curry County, so this is just Jackson and Josephine counties, but I suspect that for Curry County it's the same. So this is just a kind of a recent trend from 2005 through 2018 of the number of ignitions by year, whether it's human in blue or lightning ignited in the orange. So we tend to have more human ignitions over time, although we're getting more lightning ignitions more recently. But what I'm not showing here is that although we get a lot more human ignitions, those ignitions tend to happen in places that are easy to suppress. whereas our lightning ignited fires tend to happen in places very remote, like the Camelopards wilderness, that are extremely difficult to suppress. So that ends up contributing to the large majority of the annual area burned. So we also know our vegetation has changed because we've excluded fire successfully for a long time, and because of management and because of the Northwest Forest Plan, our forests are getting a lot more dense. This is just a quick look at basal area of trees from the Cascades, the Siskiyous, and along the coast, coastal mountains. The black bars are older trees, and the white bars being younger trees. And the story is the same, that over time, we've had a steady increase in the older trees because of fire suppression, exclusion, and then a very rapid increase in young trees as those young trees have now filled in. And then you can see that how that basal area translates into density. The same places, you can see that these are the density of trees per hectare between 1900, 1950, and 2000, where we've seen a really dramatic increase in tree density over time. That's been the same story everywhere we look. So we know we have that. We know that our forests now are heavily skewed towards young, dense forests. And we lost all of our old growth, or almost all of it. This is, again, work from Ray Davis as part of the Northwest Forest Plan, looking at the changes in what's considered old growth forest between a historic period in the 1930s, 1940s, up until 2012, with old growth, the older old growth kind of in the teal color, where it used to be very abundant historically, and we've lost almost all of it. We've converted most of those old growth forests into very young, dense forests to really change the fuel landscape. And what people have found is that, as climate is changing, those fuels, the vegetation, whether it's alive or dead, is drying out quicker, getting drier, and that is leading to a large increase in the annual area burned. So this is a comparison of throughout Western US of forest fire area burned annually, and then some measure of fuel aridity, or how dry the fuels are. So this is, the blue dots are from this time period, 84 through 1999. The red dots are 2000 through 2015. So comparing those two, we see that this recent period of 2000-2015 has seen a 3 time more annual area burned compared to that earlier period. And what they were able to do is they were able to look at a number of components and tease out what they would consider ACC, or anthropogenic climate change, that signal. So once you look at that, the climate change is responsible for 55% of the annual area burn increase over time. Another really interesting recent publication from Zach Holden and others from the Forest Service and beyond looked at trends in annual area burned and different factors that were associated with that. And what they found is the strongest predictor of annual area burned in any given year was wetting rain days during the summer period. So we've been seeing, as I showed you, a decline in summer precipitation. Our summers are down, getting drier. They found the effect of the decline in what they called wetting rain days, which I believe was a day that had more of at least 1/10 of an inch of rain or something like that. So as things dried out, you're getting more wildfire. And they found that the wetting rain day was much more effective at increasing annual area burn, or predicting that, than VPD, which is vapor pressure deficit, which is kind of a measure of the humidity of the air. And they looked at annual snowpack, and they didn't really see much of a signal, although it is contributing. the lack or the decline in snowpack is not contributing that much to annual area burn. It's really the decline in summer rainfall. And that is expected to increase. So looking now some modeled fire potential. And this is some looking at the potential for what they call very large fires, or very large fire potential, VLFP. This shows you kind of the different periods for what's called the Western Cordillera, which would include Southwest Oregon. So this is showing you the historic period in gray down here throughout the seasons and the relative change in that potential. So historic period compared to the future period, this 30-year period from 2040 to 2070 projects a large increase in wildfire activity in the summer period. And then this over here is a scatter graph of that same thing, showing you the different results of the different climate change, global climate models. So lots of variability, but showing you that amongst the Western US regions, that this area, including Southwest Oregon, is amongst the highest in predicted increases in wildfire activity. Now, this is the results of what's called the MC2 model, which is it's a vegetation model. It's a dynamic simulation model that can incorporate changes in climate and fire to predict what kind of vegetation is going to exist on the landscape. So this was done for Southwest Oregon. Although this represents actually the entire western side of the Cascades for Oregon and Washington. And this compared the historic period, which was 1895 to 2000, and then the future period, which is this century. So this is historic period. The mean fire return interval across the entire western Cascades was about 80 years for, this is Forest Service and non-Forest Service. Now, if you look towards, compare the historic to future, under those two scenarios I talked about earlier, that the fire return interval is expected to be reduced by roughly 50% or more. It was going to go from an interval of 80 years to an interval of about 40 to 50 years. Under the best case scenario. Now, the worst case scenario even get more frequent. So that interval is going to decline, which means fire is going to get more frequent. Well, this is another model that tried to look at, how much more fire are we supposed to get. So this is, it's a guess, but it's probably a pretty educated guess, and the percentage expected increase by the end of the century in annual area burn. So here in Southwest Oregon, we're in the 300 to 400% increase compared to historic conditions. So now this goes back to some of Ray Davis's work with the wildfire suitability data set I showed you a while back. But now this is taking that same data set and then projecting that into the future based on changing temperature and precipitation. So this is now trying to model wildfire suitability present and future. So now this is the suitability, that same from low suitability to high, from 0 to up to 93, showing you how suitable areas are, with the coast being pretty unsuitable, but interior, the Kalmiopsis and parts of the Applegate and others being much more suitable. So based on recent past climate, year 2000, that's what we would expect, and then we jump ahead to 2100. Not a huge change, I'll toggle back and forth, so that's 2000, and then 2100. I can see the coasts, things just jump up a little bit. They tend to get a little bit more suitable. Not a dramatic shift, but things are expected to get somewhat more suitable for large wildfires in the future by the end of the century. So that's just a quick snapshot of the years. So the mean suitability for the year 2000 for this 3-county area was 41 suitability rating. It's supposed to jump to 52 by 2060 and then to 58 by the end of the century. Okay, so again, and as I said, the proportions of fire severity have not shown an increase, but this model is telling us that it's going to happen eventually. So on the best case scenario and worst case scenario, we're going to get an uptick in the proportion of high severity within any given fire. So right now it accounts for 10 to 20% of fires. They predict by the end of the century that high severity is going to account for 50% or more of all fires. So some things to think about: drivers of changes in fire regime. Some research has found that over the last several decades, we've seen again a large increase in the number of fires and a large increase in the total annual area burned. And that increase has been linked to several things: rising temperature, more drought, longer fire seasons, earlier snow melt, and as we saw earlier, decline in summer precipitation. And this trend in fire frequency is expected to continue as long as, of course, we have the vegetation to burn. So quick, that's all wildfire. So I haven't really gotten much into insects and diseases, but we do expect that as conditions dry out, as vegetation becomes more stressed, there's a lack of water, that the incidence of insects and disease is going to jump up. So this is a prediction based on dozens of individual insect and disease models that affect different tree species. This is the projection in total basal area loss that's going to occur by the end of this period. So by 2027, we expect this much basal area loss from diseases and insects. So again, highly variable. It's pretty low in the Kalmiopsis because there's not a whole lot there. But you can see towards the coast, it's expected to see a lot of basal area loss, and even much more on the east sides and some of the higher elevations of the Siskiyous. Quick look at projected changes in vegetation. This is a look at what's called climatic water deficit, which is really going to be a driver of vegetation health and how much vegetation the landscape can support. So it really tells you how dry conditions are. And this is telling us that by the 2040s, that deficit in water is going to increase dramatically, and then even increase more by the end of the century. So what do I mean by it? So climatic water deficit is the deficit between water demand and water supply, essentially. So if you can think about our Mediterranean system, our trees have, it's warm, there's lots of sun in the summertime, that's their optimal growing season, right? But without water, they can't grow nearly as much as they would if they could. So that deficit is the difference between how much they can actually grow given the water supply and how much they could grow if water was available. So that's the difference, is this deficit. So come late summer, because of the lack of water, vegetation start to shut down. They start to really slow their growth rates, and they would be growing much faster without it. So this deficit is expected to increase. So because we're going to get less rainfall overall and less summer rainfall, so conditions will be drier, vegetation is going to get more stressed, more likely to die, and grow more slowly. So this is the results of a model that was created for California, but that includes a little bit of Southwest Oregon. And this tells us the predicted difference in this deficit in water between the historic period, recent past, and out to the end of the century, based on the best case scenario, the RCP 4.5. So this is telling us that we expect that deficit to increase, that is to get drier moderately, varying from 5 to 10% increase in yellows up to the kind of the light browns, 10 up to 20% increase in that deficit. Best case scenario at the end of the century. Worst case scenario, end of the century looks worse. So that deficit is going to increase now, jump up to 30 to 40, 40 to 50% increase in that deficit, meaning much drier conditions. Another interesting model called the Landis-2 model. A group of researchers recently published this. They looked at the Klamath-Siskiyou area. They extended into California, but this is the portion of Southwest Oregon with Brookings here and then in Medford here. So this model, what they did, it's a simulation model. It simulated kind of broad vegetation types, and it simulates processes of regeneration, of tree growth, of tree death, of fire, and other disturbances. So based on contemporary climate, today's climate, this is what they would predict the vegetation distribution would be in kind of these broad vegetation types. Tan oak, light green to kind of the Klamath mixed conifer, which would be Douglas fir, white fir, and dark green. High elevation ones in light blue, maybe the red fir, mountain hemlock, etc. And then shrubs, shrub-dominated or chaparral systems in yellow. Hardwoods kind of in the brown. You don't see a whole lot there, but that's what they would predict under conditions of a normal, not fire-excluded system. And then if they were going to project that up to towards the end of the century based on the worst case scenario, this is how things change. I'll toggle back and forth so you can see that the blue goes away almost entirely. We lose the high elevation forests. And it's hard to tell, but here kind of it's a summary based on those two time periods, that the area covered in this region in hardwoods goes from about 5% down to 3%, so a little bit less hardwoods. But we see a big jump in chaparral, which is what we would expect. So as things warm, they're going to become more suitable to chaparral. Mixed conifer doesn't really change. It kind of shifts around. The total area doesn't change, but we do we're expected to lose that high elevation conifer vegetation. And then grasslands are supposed to stay about the same. Under a non-fire excluded system, of course, our actual grasslands are a lot less than this because we're very effective at excluding fire. So yeah, so they, based on increased temperature, increases in climatic water deficit, and more fire, it's going to lead to kind of a reduction in post-fire regeneration of conifers. We're going to see more of a transition to more shrub-dominated systems and a loss of those high elevation species. So what are we doing to help manage and kind of help ourselves adapt to changing climate, in today's climate and the future climate? Well, it's called climate adaptation, and you can read more about it in that report by Jessica Lofsky and others that's now available. So there's 3 strategies to helping to adapt our human systems and our living systems to changing climate. We can try to resist. We can try to keep things the same as they are. So we might want to do that in cases like special status species like the northern spotted owl, or the pika, the high elevation pika, or white bark pine, or these are potentially very sensitive species to changing climate. So we might want to, at least for the short term, try to resist changing climate and do whatever we can to keep these species on the landscape where they are. But if you think about it, this is really only a short-term solution. Long-term, we're probably going to lose at least some of these species. We just can't resist for very long. Another strategy is resilience. So trying to make our forest or landscape more resilient to the changes that are occurring that will come. So an example of resilience would be to thin our forests. We know, and I'll get into some examples, that forests where we reduce basal area tree density, they're going to be healthier, they're going to be much more likely to withstand drought and changing conditions. So that's helping those forests to be more resilient. Or we can go with a transition response, where we can actually, we know change is coming and we actually help to transition the landscape to where it wants to go. So an example would be more oak forests. This is an example of a Oregon oak forest, low elevation. We're going to expect that in a future warmer, drier climate, that it's going to be more suitable to Oregon oak. So, after disturbances, we might actually try to assist the landscape to shift towards those vegetation types that are going to be more suitable. Okay, managing for climate resilience and transformation. So if we're going to exclude resistance now, and we're looking at resilience and transformation. So in order to prepare the landscape for future climate, things we would want to do and we're currently doing. So thin our forests. We know historically they're a lot more dense than they used to be. So we can thin to reduce competition, and not everywhere, but in appropriate locations. We want to promote late sterile forest habitats that we've lost, and those late sterile forests tend to be more climate resilient, more fire resilient. We want to favor drought tolerant species. We want to favor those species that are going to be tolerant to fire, because we know a lot more of it's coming. And we want to restore the structural diversity that we lost, because we really homogenized the forests over time. So again, example of thinning. So, thinning can be a little or a lot. So reducing competition, increasing survival rates of trees. And there are some other benefits. So this is an example from the Cascades that shows us that as they thin the basal area of these stands, of these managed kind of younger stands, that the cover of different species in the understory of shrubs and vegetation, herbaceous vegetation in the understory, increased. And a lot of those species were either drought tolerant, fire tolerant, or heat tolerant. So added benefit, if we're going to reduce canopy cover by reducing the density of trees, we're going to get the benefit of kind of increasing the cover of some very beneficial species for wildlife, and they're going to be more resilient to changing climate. And then post-fire, that was pre-fire. So post-fire, so once we have a fire, what do we do? So if we're going to replant, we want to use appropriate seed zones. So not necessarily planting the same genetics from the same location. We want to maybe plant trees that are adapted to a slightly drier climate. So we're going to use what's called seed zones to grow seedlings and then plant them, seedlings that come from seeds from a slightly wetter or hotter, drier or warmer area. And some of the strategies that have been written about, we don't want to necessarily plant in a grid. Overall, we want to plant at lower densities, because we know the landscape is just going to support higher density of trees. But we can cluster planting, higher density planting in those cooler, wetter microsites that can actually support that. And we want to try to focus on planting the drought tolerant species if we do any planting at post-fire. So some examples of some real world implications of high densities and increases in climatic water deficit. If you follow the story down in the Sierra Nevada, that in the the drought, the 2012 to 2015 drought, that's kind of still occurring, but during this time period, there was a lot of mortality of trees, especially in the lower mixed conifer zone. So over here, it's telling you the amount of basal area that was lost, color-coded, dead trees per kilometer. This is the density of dead trees. So the lower mixed conifer zone saw upwards of 50 to 75% of trees died at the end of this period. And the mortality, the amount of mortality was highly associated with basal area and climatic water deficit. So the drier the conditions were, the greater the loss of trees, and the more dense the forest, the greater the basal area, the higher the mortality rate. Again, real world example that shows you what happens if you have dense forests and dry landscape. And we have some great research to help inform this. So we know that reducing tree density reduces competition, increases the growth rate, makes them more resilient to insect outbreaks and disease outbreaks. So this is a comparison of treated versus untreated stands in ponderosa pine and Douglas fir stands, showing there that the treated stands where they've thinned are much more resilient to drought based on their growth rate and mortality rates. But that doesn't really occur until 3 to 4 years after treatment. Scatter plot of another research study from Western US, I think this is Oregon and California, that shows the trees per hectare, so the density in a particular stand and the number of trees killed during drought years. So again, generally, as you get more trees, as the density increases, you're much more likely to get a higher mortality rate. So we want to reduce that competition, and we want to make trees healthier, more likely to survive. Same thing here from another study shows that what's the SDI, the stand density index, which is a measure of how dense forests are, as that increases, the proportion of the trees within that stand that die increases. So we want to reduce that. Fire severity. So if we want to reduce fire severity, we know we're going to get more fire and likely to get more severe fire. Not that severe fire is a bad thing. I mean, severe fire is a component of the landscape that we want to keep there, but we just don't want too much of it. So we know from research on fuel treatments and how effective they are that if we want to reduce the amount of high severity fire, that we really need to thin the forest and then follow that by a prescribed fire. Doing one or the other isn't nearly as effective at reducing the amount of high severity fire. So if we want to do that, I mean, we want to do that in some locations, we know what we need to do. Again, this is showing proportion survivorship of trees in untreated versus treated. So a much higher survival rate of trees in treated stands versus untreated in different places in I believe this is in Sierra Nevada. And this is kind of complicated, but it's just, this one's showing you that treatments don't always work out as planned. So this is an example from Washington, Eastern Cascades of Washington, that shows that thinning and pile burning actually had more high severity and less high severity than just a wildfire itself, previous wildfire. So it doesn't always work out as planned, but so we just need to be careful. And I'm almost done. I know there's just a couple more slides and we can take questions. Another thing to think about is climate refugia. So as we know, things are going to dry out, get warmer, get more fire. We want to identify those places in the landscape that are going to tend to remain cooler and or wetter in the future, that are going to be pockets where we can maintain wildlife and vegetation, where it's not going to change or not going to change as quickly. So yeah, so those areas that kind of escape, at least for a while, those adverse conditions tend to be cooler, wetter, where cold air tends to pool. So this is some interesting research from the Sierra Nevada with, I think it's the Belding's ground squirrel, that looked at various measures of what they would call climate refugia, and either the absence or presence of those squirrels. So the squirrels tended to be present in areas that were cooler, Yeah, cooler, wetter, and had more snow. So that's true of wildlife. And another interesting research study found that climate refugia tend to be coincident in space with wildfire refugia. So the places that are going to kind of stay cooler and wetter, of course, you would expect to be more resistant to wildfire. And this research found just that where a cold air pool was present, places where they're going to be cooler in the landscape, that the proportion of higher severity fire was much less than would be expected. So it tends to burn at much lower severity. So another reason we want to protect those areas. And this graph shows you the results of wildfire effects on different forest types or structural types, from non-forest through kind of the closed small trees, kind of a dense young forest, a dense medium-aged forest, and a kind of an old growth forest. And the blue part of this graph is telling us the amount in those forest types that burns in very low severity. So it tells us among the forest types anyway that the old growth forests with big trees tends to be the most resistant, tends to burn at the lowest severity overall. So we want to identify these locations, treat within them, potentially, treat without them, treat around them, to try to protect them from wildfire if we can. And we want to reduce other stressors that can be, making matters worse. So, we know climate's changing, fire's changing, so we want to try to reduce other stressors that are making matters worse for vegetation and wildlife. So we want to control invasive species such as cheatgrass. Cheatgrass isn't much of a problem here. It's really a problem in the kind of the basin and range portions of the western US where cheatgrass is invaded. It's an annual grass, and it really increases fire activity, can really increase fire activity and make matters even worse. So we want to kind of control those species. We want to, here's another example of some knapweed, spotted knapweeds or Japanese knapweed that can invade places and stress other plants. We don't want to reduce that stress. Now, if we're going to replant, we want to plant disease-resistant trees. Down in Southwest Oregon and throughout the West, we have a big problem with white pine blister rust. So we're losing our white pines. So when we do planting, we want to plant with resistant stock, and we have some of that available. And we know that we want to protect those areas in the landscape that are going to be most resilient to changing climate, as I said. So this is a great data set that we're using, developed by the Nature Conservancy, that looks at total landscape resilience to climate change, which is a function of kind of the geophysical diversity, which is called the stage, which is the diversity in parent material in the geology and the soils. Combine that with topoclimatic diversity, so that's diversity in the topography, in elevation and slope and aspect. And then you also combine what's called landscape permeability, which is either the presence of or lack of artificial barriers that would inhibit movement of wildlife. So when you combine those all together, you get what's called the landscape resilience to climate change. And this shows you areas in kind of the teal or have very high resilience to changing climate versus areas in dark brown that have very low resilience to climate change due to either lack of diversity in these or more barriers to movement. And finally, last slide, another great data set we're using that was developed that looks at identifying climate refugia. So this uses an elevation model and factors in solar radiation and heat load based on slope, aspect, and latitude. And then calculates the effect of sun exposure and topographic shading on that potential rate of evapotranspiration I talked about earlier. So this is showing us across the landscape. This is part of the Applegate Valley. Those areas in blues, which are expected to be the cooler microsites, which we might identify as climate refugia, or we might want to do some different kind of managements and treatment around that, versus the kind of the darker reds. Those areas were expected to be the driest in the future, places where we might actually want to transition vegetation into grass dominated or shrub dominated, something like that. So I think that's all I had, and I can take questions now.
All right. Well, thank you, Bill. I appreciate that. You've provided an awful lot for us to be thinking about and all. And we did have a number of questions. There were several that kind of focused in on the same thing, a little bit about what you were talking about before. What I'd like to do is I can read the question, but Alan, if I could, I'll unmute you and ask you to ask your question in terms of the forest management, and is particularly with respect to inviting Bill for climate smart management principles.
Yeah, I know. I've known Bill for months, so we go back a long way. And Bill and I have been working on we call SOCS, the Southern Oregon Climate Smart Working Group. And so I just wanted to invite Bill to talk a little about how climate smart relates to everything that he's been talking about. Without putting him on the spot is my.
Oh, look, I mean, yeah, we're trying to be smart about managing forests in a changing climate. So that's using, I talked about it a little bit, we're using principles of conservation in a changing climate to prepare the landscape for coming changes, to be ready for more fire, to be ready for drier conditions, using available data, using available models to help us kind of not necessarily resist, but make the landscape more resilient, or to help it transform into systems that are going to be much more resilient to today's climate and tomorrow's climate. So, the forest is thinking about that, using available data, using available science, and using the help of this group that Ellen mentioned, the SOCS group, to help to try to inform their planning process, to try to incorporate more thinking about climate resilience into actual planning when they write a planning document like an EIS or EIR. Yeah, to start to think about that stuff up front throughout the whole process. Will that cover it, Alan?
Yeah, that's pretty much where I was.
Okay.
Thank you.
Bill, I'd like to sort of follow on that. I know that there's a big push for quote, management of the forest by the commercial operators that want to do the logging. What's the right way to do the balance? What is intelligent forest management? How does that fit with logging? I guess, put it most simply.
Well, logging is something the Forest Service provides. It's a mandate from the Forest Service that each forest provides a certain amount of timber volume every year. So it's something the Forest Service has to do to support local economies. So we're going to continue to do that. So we just need to figure out where and how to do that. So my role, and with other specialists, is try to figure out, okay, what are the current conditions on the landscape? How do we expect things to change? And if we're going to take volume out of the forest, where do we want to do that? Where are the priority areas for doing that, and how do we want to do that? We want to do our best to leave the big trees in the landscape. Those tend to be much more resilient to changing climate and changing fire regimes. So we want to try to leave the big trees, but we want to try to thin from below, really. Removing the ingrowth, the smaller trees, and the less climate resilient species like white fir that have filled in, that we can remove and make those stands healthier for the long term. And try to try to introduce fire when we can. We're trying to do as much prescribed fire as we can. You know, the Forest Service just doesn't have that much capacity to do a whole lot of prescribed fire, but we do as much as we can. So we're trying to introduce fire back into the system as much as possible.
Okay. Well, let me get into another question. Chris Stanstead had said, Chris, I'll just read it for you as well. But how does all the private forest land owned by timber companies figure in? Reducing density seems counter to their business activities. Kind of fits with that.
Yeah, unfortunately, yeah, as people have said, you know, a lot of those industrial forest lands are just owned by investment groups. So they're just looking for a quick turnaround, a bottom line, you know, a profit over a short term. But, you know, as researchers have found that there was a great paper by Harold Zold and Chris Dunn that found that, you know, those highly managed, dense industrial forests tend to burn at higher severity when they do burn. So, you know, as we get more fire, they're going to lose their assets really quickly. So, you know, that's not the answer. So I think, you know, knowing that, I would hope that they're going to start to change their practices to make the lands they manage more resilient to changing fire and changing climate.
That would be nice. It seems like that requires an appreciation for data and science, and hopefully at some point we'll get back to that. But
yeah,
some interesting challenges. Another question was about grazing. It said grazing seems to make fires worse. Is that right? The right conclusion? That was from Deb Worth or Ed?
It depends. I mean, it depends on what system you're in, but, you know, grazers tend to graze down the herbaceous layer in the understory or in a grassland. So, on a local scale, you know, they're reducing fuels. So they're going to reduce, you know, the available fuel in that layer. They're going to reduce spread rates where you have a lot of grass. You might have a lot of grass. Yeah, I'm not aware of where grazing would increase fire risk, unless it's tied to invasion of something like cheatgrass, where, you know, places that are grazed a lot now they've now invaded, and you have a lot more cheatgrass with a lot more potential wildfire. But for the most part, you know, people have found that, you know, grazers, you know, they reduce that fuel level, so it's actually going to, at least for the short term, is going to reduce wildfire behavior.
Okay. Got one specific question had to do with the graph you had with respect to the increase in fire season that we've got. It was, several of us noted that there was a 3, 2 4s, 2 5s, then a 6.
Oh yeah, I noticed that too. I have to correct that. I don't know why. I think it must have been 4, 4.5, 5, 5.5. I think that just got cut off somehow.
That's what I wondered. That would make sense. So, I think that's much of it. And let's see. Yeah, we're sort of talking about density of function of management and commercial. That was taken care of, I think. My question from now, we've only a few minutes left. From your perspective, what's the best thing that we as Coastal SOCAN, can do to help you do your job of managing the forests, trying to figure out how do we get most resilience for dealing with climate change?
Yeah, I mean, I guess, you know, doing what Alan and I are with this SOCS group is just, you know, get involved early in office and in the planning process to try to, you know, make sure the Forest Service is thinking about changing climate. I mean, we should be, but it would be great to have other voices there to help us make sure we're doing that. So yeah, get involved in the planning process.
Yeah. What's the best way to do that? I mean, how is it different? Is there anything different from that we can do here on the coast, different from what Alan's doing in the Rogue Valley?
Well, you can just you can get involved in future planning locations, projects that could occur along the coast. You know, we have some long-term ones ongoing, healthy forest stuff, but we have the Shasta Agnes, which is not quite at the coast, but that one's about to be signed. But then we're going to have some future project areas out near the coast sometime in the next 5 years. Potentially, there's going to be one that's going to be really close to Brookings. So, when that happens, definitely get involved. Stay in touch with the Gold Beach Ranger District to find out what's going on.
Okay, that would be good. Had a last question sort of pop up. Is there any effect of the suburbanization of the coastal forest lands?
On wildfire or changing climate?
Well, let me actually put Berta on the spot if I can find Berta here. Unmute. Berta, do you want to explain if I can do it unmute here? Come on. It doesn't want me to unmute. I'll try to unmute everybody for the moment. Berta, can you explain your question?
Mm-hmm.
No. All right. So I will remute everybody to make sure that.
Now and see if it works.
There we go.
Am I here?
Yep.
Okay. What I'm wondering is the sprawl from the communities out into the forest lands, and how is that going to change your wildfire picture, say, in the next 20 years?
Well, as sprawl increases into the wildland urban interface, is that that interface increases, we're going to get more incidental ignitions. That people have found that throughout the Western U.S. So as development moves into that further into that landscape wildland interface, we're going to get more ignitions. It's just going to happen.
Do we know what rate that is happening?
People have looked at it, a case by case basis, around different communities and different states. So it varies, but there's definitely an increase as development increases into the wildland area. In ignitions increase, annual area burn increases. So as the counties and the state and cities need to think about, policies around development in the wildland urban interface, whether, things to discourage it, or if you're going to do it, do it in a fire safe way. Stuff to think about, because you can do it as safe as you can, but there's still, as long as you're creating more roads, more access, there's just more opportunities for inadvertent ignitions.
Okay. Well,
Thank you.
It's now just about 7 o'clock, and Bill, I want to thank you very much for giving us an hour and a half of your time. I know you've got your family there, and when we chatted earlier, we got to see your dog, and so it's nice to be able to capitalize on your experience and expertise and answering the questions, and also not have to make you drive over here to the beautiful coast, except we haven't seen the sun today, it seems like.
Oh, nice. Yeah.
So any last parting, words for us, or shall I sign off with Alan's comment about us getting involved? And for all those that you are on the chat, you can go look and see the information for everybody that Alan posted. So I recommended that you all do that. And then final words, Bill.
I know a lot of what I presented, the projections are kind of grim, how hot it's supposed to get and how much more fire we're going to get. But, there's definitely things we can do to try to make our landscape, both the human landscape and the wild landscape, more resilient to climate change. So, thinking about what you can do on your own property to make your property and your home more resilient to changing climate and fire, something you can do. And then, as I said, get more involved in the planning process on public lands to try to push them to make better decisions about forest management and climate adaptation and wildfire.
And of course, the more we can do to get away from a business as usual, or what had been considered the worst case scenario, and minimize the change in temperature, that would be wonderful. So
Yeah.
great. All right. Well, thank you very much for your time. I'm gonna end the meeting here, and we will check in with you later.
All right.
Thanks, everybody.
Thank
It's
you.
my pleasure.
Thank you.
Bye.